Hey guys, we're back. We're getting started again. So I hope that first tutorial gave sort of a glimpse of what GMAT can do in certain areas. Next, we're going to go ahead and do really spend the next hour, 50 minutes or so, really going deep into the different areas of GMAT and how it works and the sorts of things you can do with it. So we'll start by going a little bit into some key concepts of GMAT, a tour of the graphical interface, a tour of the script interface, script language, a bit in data files, configuration, plugins, and then how to get help after this class. So starting GMAT, we already know about this. I'm just going to skip it. The full view of the Windows desktop. I think, can someone put their phone on mute? I'm getting some echo back here. Thanks. All right. So here's the main graphics window, GMAT window. There's the menu bar, which we noticed, the toolbar, the resources and mission and output tabs. These are tree views. Message window, status bar. This message window is actually shows everything that GMAT is doing live in the text mode, so very detailed. 3D window and 2D window. So let's start by going over some key concepts. So, oh, all right, hang on guys, I gotta plug in my laptop. The first key concept we're going to go over is what's called the execution model. So I'm going to contend here that you can quibble with my examples, but I'll contend that GMAT is more like MATLAB than something like Microsoft Excel. And it's like MATLAB in the way that, hang on a second. In the sense that, like MATLAB, you write a program and then run it to generate output. So this is similar to if you've used other tools like FreeFlyer. This is similar to how FreeFlyer works. You basically write a script, you run it through GMAT, you generate results, and then if you need to make changes to those results, you re-edit your script, run it again, and get your new results. Okay? So this is not like a program like Excel where you perform some calculations and you have these results and then you can manipulate them in all sorts of ways. That's more the SDK model, the post-processing model. That's not really what GMAT's intended to be. GMAT is a simulation tool that runs end-to-end. So when I say a batch execution model, I'm saying you start out with this script, you run it through GMAT, you generate some output, and then again, if you need to make changes, you have a loop here where you re-edit your script, run through, generate your output again, and go backwards. So in terms of key concept 2 is what we were talking about before. We have two parallel interfaces in GMAT. We have a GUI and a script. We've been messing with the GUI, playing with the GUI at this point. We also have this script mode, and the contention here is that the GUI and script are nearly interchangeable. You can use them whichever your preference is. You can use the GUI.
Really bad. You're getting really bad. Yeah, it's getting feedback. Can everyone mute? Can everyone mute?
Yeah, thanks. Sounds like someone still has a live mic and is echoing back. All right. So when I say they're interchangeable, I'm saying that all features in the GUI are also in the script and vice versa, except for a few minor exceptions. And they're exceptions that you would expect. So there's some things in the GUI that are naturally only in the GUI. So things like interactive features, 3D window manipulation, animations, 2D plots, screenshots. These are things that obviously, when you're doing things interactively, only make sense to perform in the GUI. There's also some things that are only present in the script, and these are less things that you wouldn't expect as much. But basically, they include certain bits of advanced functionality. So some advanced force modeling, some developmental features, some plugin-only features. These things are only available in the script. And the philosophy that we use is, especially if something is not widely applicable, like a Mars atmosphere model, the Mars Gram atmosphere model, we develop in the script first. So when we develop, we come up with some scripting language, we implement it, we test it through the script, and then if demand is sufficient, then we implement a graphical component for it in the interface. So that's why there's some things that are only present in the script. It's because they're sufficiently advanced that we just haven't put in the time to make them in the GUI yet. So that's what I mean when I say new development happens in the script first, and then in the GUI. Because of echo or because of volume? Or? No. Is that better in terms of volume, everybody on the phone?
No.
Is it the echo or is it volume of voice?
Sounds like going to the mic. Yeah, it was fine this morning.
All right, let me mute for a second and see if there's anything I can do about that. Hang on a second. Do you know if there's a way to force someone to the mute on the phone?
Yeah, there is if you got the leader passcode and a website you can log into.
Is there that? I have a leader passcode. Do you know what it is?
There are certain shortcuts,
Website.
the instructions they send you. You can mute one, but you need to know which one.
Oh yeah, there may be another way you can do it on the keypad, right?
There's you need to you could probably force everyone to mute.
We're sort of consulting on our side to figure out if there's a way to get rid of that echo. Hang on a second.
Everybody wants
Try
to
star
check
4.
their mics.
Star 4.
Try star 4 and read all the gas, at least on mine.
The conference is now in silent mode.
All right. Is that any better?
You're not going to hear them because they're on mute.
All right. Okay. One of our in-person guests kindly helped me out and told me how to put the conference on silent mode. So I hope that will help in terms of echo and feedback. It does mean that if you have questions, you're going to have to use the chat feature on WebEx. So Rizwan is on there, and if you have questions, he'll just call them out, and I'll repeat them over the phone. So for some reason that is not working, tell Rizwan, and he'll stop me again. All right, thanks for the patience.
You could try it. It doesn't say actually, but you could try star 4 again to see if you can undo and just take a roll call and see if that was better.
That works for me. Thank you. All right, moving on. So, no, you can do them both. So the relationship with the GUI and the script, I'll sort of demo it in a bit, but you can sync them up, right? So if you put a script-only feature in your script, it'll just ignore it when it comes to the GUI. It'll save it, but it won't just be reflected in a panel or a checkbox or anything. So yeah, you won't lose any data by using those features. All right. All right. Concept 3 is something we've looked at here previously, but it's this concept of resources and commands. So when I say resources, if that's not sufficiently clear, resources are objects. So when I say resources are things, you can think of them like objects in a programming language. They are participants in your mission, and they are fixed. So you configure your object at the beginning of your mission, and then that object is in existence throughout your mission sequence. Okay? So you create all of your objects at the very beginning, all your resources, you configure them, and then for the most part, they're fixed while you perform your mission. There are some examples. You can obviously change your spacecraft state throughout the mission, but most times things are pretty much fixed at that point. Commands are a little bit different. Commands are events. They represent actions, and you can think of them as methods or functions if you're familiar with programming languages. Commands are the actions that occur on the resources. That's the simple way to think about it. So these two are very linked. Resources are the things, commands are the events. And some examples of this, so these are examples of resources. You have physical objects like spacecrafts, tank, thrusters, planets, asteroids. You have sort of mission level objects like burns, analysis objects like propagators, force models, coordinate systems. These are sort of conceptual things that you need to deal with throughout your mission. And you have sort of programming related software objects like variables, arrays, strings, output files, input files, all these sort of both physical and conceptual objects that you're dealing with. These are all resources. In terms of commands, remember commands are all events. Things like propagate, maneuver, you can begin a finite burn, that's an event you perform. You have analysis statements like optimize, target, vary. You can vary a parameter to achieve another condition. You have programming statements, for and while loops. The assignment command is a particular type of event. You're assigning a value to a variable. You can call a MATLAB function. That's something that we've mentioned briefly. And then output control. So you can report a value to a file. That's a certain type of command. You can toggle a plot. You can mark a point on a graph. These are all examples of different types of commands. So in general, the resources are contained in the resources tree. The commands are contained in the mission sequence. All right, and finally, the last key concept. This is sort of an advanced thing. I will be very impressed if you feel like you fully mastered this difference in this training. It usually takes some feeling out to actually figure out what the difference here is. But we have two types of data parameters, or data properties. One is called fields. The second is called parameters. Calculation parameters is another way we describe it. Fields are, fields are properties you can set, okay? So when we set the Keplerian state on a spacecraft, we were setting those fields, SMA, eccentricity, inclination, we were setting those fields on the spacecraft resource, spacecraft object. So fields are for setting things like epoch, file name of a report file, decrement mass, flag, true or false flag on a thruster. These are all fields. On the other hand, there's things called parameters that you can calculate. Okay, the key word here is parameters are things you can calculate. So things like I can calculate the altitude of my spacecraft, or the vector, or the angle of the B vector in the B plane.
Can you define new parameters from the script?
Not as of yet. So the way you would do that, No, you would create a variable, you would perform a calculation, assign it to the variable, and then you would use that in your script, in your logic.
You can do that.
Yes. So yeah, so variables, arrays, strings, these are things we call user-defined parameters. Okay. But with the true parameter, you can do things like you can say, I want to calculate the attitude with respect to the Earth. You know, it just happens naturally. The analog to that for a user-defined property is to call out to a function and return back. So the conversation I was just having was mentioning dependencies. Parameters often have dependencies. So here I'm calculating the attitude with respect to the Earth. I'm calculating the B vector angle with respect to the Earth J2000 coordinate system. So the key difference is fields are settable. Parameters are things that you calculate live. The confusion is sometimes a property can be both a field and parameter. For example, you can set the SMA of a spacecraft. You can also calculate it with respect to Mars during your mission. Same with fuel mass. You can set your fuel mass at the beginning. You're setting, I have fuel, 1,000 kilograms of fuel. You can also calculate it during your mission. I have 500 kilograms left. Okay. All right, so that's the hard part. I'm going to go ahead and give an example now of, so I tried to intersperse some of this conceptual stuff with live examples of things we've done. The mission called LCROSS is a lunar impactor mission. Anybody here work on LCROSS? No? Okay. Steve Cooley, who's here this afternoon, worked on it heavily, so you can ask him questions about it. But it was launched with LRO. It rode with LRO on its outbound trajectory to the moon. LRO went into moon orbit, or lunar orbit, and LCROSS detached from LRO and went into a highly elliptical Earth-centered trajectory for a few years, I think, and then came back and in such a way that it impacted the south pole of the moon as LRO was crossing over, so that LRO could measure the material ejected from the impact zone. Is that...
3 months or so.
Okay, 3 months. All right.
In June and impacted in mid-September.
All right. So it wasn't years, it was months. Yep. So GMAT, I'm going to show this example here and show you what we did. But we basically, during the design of this, do you remember what year it was?
2009.
Okay.
Launched 5 years ago.
Yeah. So in the 2008-2009 timeframe, we used GMAT to help optimize the lunar flyby that LCROSS did in order to achieve the correct impact parameters on the moon. So this is a highly nonlinear regime. We used GMAT in a segment-based analysis where we placed one segment on the outbound leg, put one segment at the impact, propagated them one segment forward, one segment backwards, and imposed a matching constraint in the middle. And then we used an optimizer to change the properties of the two endpoints while maintaining continuity to minimize fuel, I think, in this case. Yeah, it says minimize, to minimize fuel. And then we did some launch window analysis using GMAT and Copernicus. So what I'm going to show you is this example LCROSS.script. Folks on your computer or at home, you can actually load this. It's in the examples folder on your desktop. And it will show you a recreation of the optimal trajectory. The reason why we do that is it takes a long time to actually solve the optimization, and it's not available publicly anyway. So the better thing to do is just to simulate the final solution and then demonstrate that. All right, so if you're doing this on your computer, you have GMAT open. You can click the Open button here. I'm going into the GMAT Fundamentals folder and examples. And we're going to look at the LCROSS trajectory.script. So it's asking me, do I want to save, the script from the previous tutorial? I say no. And now it's opened. So let me just run it and we can sort of talk about it as it's going. So what you're going to come up with is two 3D graphics windows that both simulate simultaneously. The top window is showing an Earth-centered view where the gray circular trajectory is the moon. The red spiral trajectory is LRO in lunar orbit. It's just going around in a spiral. And green is the LCROSS trajectory that you'll see it's going along with LRO here at the beginning. It performs its lunar flyby here, and now it's in a highly inclined Earth orbit while LRO continues in its orbital trajectory. And I'll just pause it while I explain further. All right, let me draw. So here's Earth. Here's the moon. Okay. Here's our flyby point. And the red is LRO. And the green is LCROSS. So like I said, the optimization was performed in order to optimize the properties of that flyby such that the impact occurs as we want it to. I'm just switching over while it's paused to the other window so we can see what's going on. This is an Earth-centered view. You can see here in the lower corner, moon inertial. So the coordinate system of this view is moon-centered. Here's LRO. Here's LCROSS. And we're looking at the South Pole here. So I think we're going to get, there's going to be an impact in about that region. So we'll continue the run. And we see the impact occurring October 9th, 2009. Okay, so replaying it, you can see the flyby happening here. Speed it up a little bit. The reason for the flyby is to create this highly, see the inclination change between that? That'd be hugely expensive to do with propulsion, so that's why we do the flyby. So it looked like that was about July-August timeframe of '09. See the moon and LRO going around in the back. And of course, our October 9th date shows the impact at the lunar south pole. Question about that example or how it was done? Yep. LRO is red. Yeah.
So it looks like there's a bunch of like humps.
This right here, these sort of discontinuities.
I don't know if it's that.
It's on the other OrbitView window. Right there, yeah, the red,
Yeah.
Oh yeah. So if you zoom in, these are lunar orbits when viewed in a Earth inertial frame. So see if you zoom in enough, you'll see the LRO spacecraft right there. It's just an artifact of, because we're not Earth or Moon centered. So the Moon's going along and then it's doing a spiral thing. It's kind of interesting to see it that way. And the sort of jumps here, see how it's not smooth? I believe that's caused by, this gets just into how the OrbitView is plotting things. It's plotting things, I think, according to LCROSS's time steps. So LRO is a little bit disjointed as it goes along.
we have a question, are the windows supposed to animate independently?
Yeah, so the question from a remote participant was, basically, can you animate both windows at once, or are they independent? The answer right now is they're independent. So I can start animation on this one, and then I can start animation on this one separately. I believe there's a feature request in there to have like an animate all button or something that does them both, but that's currently not possible.
When you pause it in the middle there, how can you reset it and then start it? I guess when you're done.
Well, that gets back to one of his questions. GMAT is actually built to answer your question. So you would animate, you can stop it, you can start it again, and it'll start from the beginning. What we don't have is a true pause button that lets you pause an animation and then resume from where it starts. So I think it's doing what you were asking for. You can pause a run though. So these here are the, yeah, so these are the run controls versus the animation controls. You can pause a simulation midpoint and resume it. The idea being that you have a long optimization sequence happening. You want to, if it's doing something funky, you want to stop it, pause it, analyze the current state of things, see where it's going wrong, maybe resume it, maybe reset and change some things. So usually the simulation is the most time-consuming part. So that's why we have a stop and a pause at that point. All right, so I'm just going to go over some parts of the GUI right now. So I think we mentioned all this. The only one I didn't mention was this this help buttons. So click help. That's a good way of getting access to our full, 700 pages of user material. The resources tree. So we've messed with this before. The only thing is you can see it's divided into folders here. Here's your solar system. You click the plus button there. You can expand the solar system, see all your planets and bodies. The mission tree, of course, contains all your commands. Contain lots of commands. We didn't touch on here that these controls right here can help you filter out a lot of commands you may not be interested in. So for example, here's filtering. You can collapse by 1, 2 to 3 levels of depth in terms of your nested statements, loops, and things. These buttons will show only certain things, like This will show only physical commands like propagate, perform or burn, only things that physically occur. This one will show only solvers. This one will show only script-related statements. And these buttons will exclude certain things like exclude reporting, exclude function calls, just to get a better picture of your mission sequence. The output tree is pretty simple. This just contains links to all of your output reports. Here's your OrbitView and your ground track plot. If you recreate reports, they'll show up as a list under reports in the ephemeris files. For OrbitView, again, this is stuff that I've covered already. It's your 3D graphics window. We do have an XY plot that I haven't gone over yet. That's for 2D plotting, X and Y plotting. And we have a ground track plot for mapping. Here's the mouse controls that we were asking for before. Left button, right button. And here's a rotation normal to the screen. If you get things sort of misaligned, you can use the middle button to orient yourself in the plane of the screen. And then configuration, camera controls, what to draw and what visual elements to include, axes, coordinate system, related things, stars, constellations, etc. So a good way to highlight all that is to show this example. So this is showing what's called a safety ellipse relative motion simulation. So if you can't see the screen very well, you can open up in examples folder the ex_safety_ellipse.script and hit run. So what this is showing is you have a spacecraft okay. You have an invisible spacecraft at the center of this coordinate system. You have a follower spacecraft there in the screen that's actually being modeled. And what we're showing here is the relative position in the V&B frame, velocity, direction, normal direction, binormal direction, of the follower with respect to the leader. And what we're simulating here is what's called a safety ellipse, which I'm not a relative motion guy, so I'm going to get this slightly wrong, but if you have a following spacecraft approaching a leading spacecraft, you want to design your relative motion such that if you lose control of the follower, it doesn't impact the leader. So you don't want to just put yourself on a trajectory that's going to have an impact with the leading spacecraft, because if suddenly you can't burn to get out of the way, you're going to impact, and that would be bad. So instead what they do is they approach the leader with the following spacecraft in an ellipse, such that if you lose control of it, it will spiral out past the leading spacecraft and not have a conjunction. So the simulation here is basically showing that you can configure your 3D graphics and your simulation to run entirely in a relative space instead of an inertial space. So here I'm plotting the following spacecraft. For folks on the phone, it looks like WebEx is being pretty laggy, so you might want to run this on your own computer. But we've defined the coordinate system and the spacecraft state to be entirely relative to the leading spacecraft. And so we're basically viewing it in its natural state of showing an ellipse in that relative motion environment. So when you look at the whole trajectory, it looks like what you would expect, sort of an approaching ellipse towards the leading spacecraft. Now, if you did this all in a inertial environment, it would look just like I mean, this is it inertially. It's just looks like an orbit. You can't tell that it's doing anything special. And the way we've done that is for the relative windows, we've simply defined things such that the coordinate system is V and B, reference to the leader, and we're putting the camera 2,000 kilometers away from the leading spacecraft in that V and B system. So that's just an example of sort of the flexibility of the graphics. Just to show the coordinate systems, here we've created our V and B system. So here's our V and B coordinate system definition. The origin is the leading spacecraft, so you can actually put the origin of a coordinate system on another moving object. The type is something we call object referenced. So we're saying the primary object here is the Earth, the secondary object is the leading spacecraft, and our axes are defined such that the x direction is the velocity, the y direction is the normal vector, and the z direction completes the right-handed system. So that's defining a V and B coordinate system centered on the leading spacecraft. And once you do that, you can do very powerful things by just defining your views relative to that system, and everything flows naturally. Looks like it's not done this way in this example, but we could actually define our orbital elements relative to that V and B system and say I want to position myself, 10 kilometers in the x direction and 20 kilometers in the y direction, all relative to that leading spacecraft. Any questions about that example?